We're going to talk about thermodynamics in this chapter. And thermodynamics deals with a number of things, but a lot of times it does deal with sort of spontaneous and whether or not a reaction will take place. You talked about in Chem 50 already, sort of the first part of thermodynamics, which is the conservation of energy. And that had all that stuff to do with our delta H, right, which is our enthalpy. And remember, as we've done before, delta H, right, if it is negative, once again, is a exothermic process, which means heat and energy is released. If delta H is positive, it's an endothermic process, which means that heat and energy is absorbed. So that's sort of the first law of thermodynamics, the sort of conservation of energy, where energy is neither created nor destroyed. And as you probably learned when you dealt with really all that sort of delta H sort of information, the idea of what we deal with a lot of times is pretty much the idea of you have sort of a system and everybody else pretty much outside of that system is the surroundings. And when we have something like heat and energy being transferred, we oftentimes think of it as sort of a perfect transfer. So that what that means, for example, is if your system gives off a certain amount of energy, then your surroundings should absorb the same amount of energy. The actual value for the energy would be the same number, but the sign would be different, indicating whether it's being lost or absorbed, and vice versa. If the surroundings should sort of release some energy to the system, then the system would pick up that exact same amount of energy. So that's sort of the idea of this sort of the conservation of energy. Energy definitely can be transformed from one place to the next. But overall, we still have sort of the same total amount of energy that occurs. So in this chapter, what we're going to look at is some other letters of the alphabet. After looking at K for so long, we will look at our H's here. We will look at entropy, which is delta S. We'll look at free energy, which is delta G. We got to use a little bit more of the alphabet here in this chapter, so that's nice. And then, of course, we will find our good friend K at the end there and come back to equilibrium. So let's first talk about the idea of spontaneous physical and chemical processes here. And all these processes that we see here on this list, they're all spontaneous processes. And something like waterfall runs downhill. So usually the water doesn't go uphill. A lump of sugar dissolves in a cup of coffee. At 1 atmosphere, water will freeze at 0 degrees and ice will melt. Heat does always flow from sort of the hotter object to the colder object. Iron exposed to oxygen and water will form rust. So obviously coming downhill skiing is a spontaneous process, right? You pretty much just need to kind of go over the hill. A non-spontaneous process would be if you decided to go uphill and you're at the bottom, probably freaking this guy out as he's coming downhill, I'm imagining. So what we deal with a lot in sort of thermodynamics is really talking about the idea of whether or not a reaction is spontaneous. And sometimes people have a misconception about the idea of what spontaneous means. Sometimes, a lot of times, people associate spontaneous with meaning it occurs like super fast, like it's spontaneous and it occurs. And that's really not what we're looking at here when we talk about thermodynamics or we talk about a reaction being spontaneous. What we're talking about here in this sort of chapter is the idea of if it is spontaneous, what that means is under those particular conditions, we would expect this reaction to actually occur. So it would spontaneously occur, should occur by itself. If it is non-spontaneous, what that means is under those conditions, the reaction would not occur. It really has nothing to do with how fast or slow a reaction occurs. And what deals with that is what we talked about at the very beginning, which is kinetics. So kinetics deals with how fast or slow a reaction occurs. Thermodynamics really deals with whether or not sort of the reaction will take place. So here's a couple more examples: spontaneous, non-spontaneous processes. Obviously, if you open the valve here, spontaneously these gas molecules would fill across the tube there. In a non-spontaneous thing, if this valve was open, probably they wouldn't all kind of go that way. You would probably have to do something to it there to maybe encourage those gas molecules to head that way. But under a spontaneously, they probably all want to go back to the other side. So when we talk about a reaction being spontaneous, as I mentioned, it does mean whether or not that reaction will take place. You can have a spontaneous reaction that is like super slow. It just means eventually it will take place, but he might have to wait around for a long time. That's why they invent things like catalysts, right? That speed up a reaction. So that helps the reaction occur a lot faster. The other sort of thing that we sometimes think about, and maybe is sort of a misconception, is the idea that a spontaneous reaction needs to be exothermic. Like it has to be exothermic, has to be releasing energy for the reaction to take place. And all these reactions down here on the bottom, they're all spontaneous reactions. So we got a combustion reaction with our exothermic. We have the formation of water, which is exothermic. We have the melting of ice, which is actually endothermic. And we have this guy, which is basically dissolving a solid. So in certain cases, as we see here, some of these processes here are exothermic. Some of these processes are endothermic. But you could have a spontaneous reaction occur, whether or not it's endothermic or exothermic. Probably the easiest one to visualize is the ice cube example, right? You take the ice cube out, you just drop it there. It is going to spontaneously, right, start to melt because it's picking up the energy from the surroundings, right? Which is an endothermic process for the ice cube. And it definitely would occur spontaneously as you make a mess all over the place. So exothermicity, or a reaction being exothermic, it does obviously favor in a lot of cases the reaction being spontaneous, but doesn't necessarily guarantee that it will be spontaneous. So what we do have to look at is some other sort of properties to help us decide whether or not a reaction will be spontaneous or not. And one of the things that we could kind of look at is entropy. And entropy is delta S, and that is the change in entropy, not to be confused with enthalpy, which is delta H. So enthalpy is delta H, which is the energy. Entropy is actually the measure of randomness or disorder there is in the system. And entropy kind of works a little bit different than that's sort of how we envision enthalpy working. As we increase the order, the entropy actually decreases. So as things get more ordered and we create more order, less disorder, however you want to think about it, we actually end up with a more negative change in entropy that occurs. When we increase the amount of disorder, and there's a lot more disorder happening, the entropy value actually increases, and it's actually a more positive value. How do we calculate the change in entropy? It's obviously the difference between products minus reactants, our final minus initial sort of states, to give us our entropy value. The easiest thing to sort of visualize, or one of the easiest things to visualize in terms of entropy and disorder, is actually the changes in state. Obviously, as we go from solid, where everybody is packed in pretty tight to one another and pretty ordered, to liquid, where they're still relatively packed in tight to each other, but a little bit more room for movement, to gas, where they are completely broken apart and flying around. So as we go from solid to liquid to gas, we are creating more disorder. Things are moving around more, right? Things are flying around, definitely when we get into the gas. And we would expect the delta S value to become more positive or be really a positive change in that case. Opposite is true as we go from gas to liquid to solid. We're creating more order. Things are becoming more ordered. We're decreasing the disorder, and the delta S value would become more negative in that case. Any questions on that there? So if we look at this, we can make a relatively good prediction as to what we would expect to happen with our entropy value. This is basically ice melting. So when ice melts, are we going from more order to less order? We're going to end up with less order, more disorder. You should probably choose one of those words to use as you think about these things, either disorder or order. So in this case, we're actually increasing the amount of disorder, right, in the liquid state. That means our delta S here would end up being actually a positive number when we would calculate it. The other sort of important thing about sort of difference between S and H is actually units, as we will see. Typically speaking, S is in joules, and typically speaking, delta H is in kilojoules. So there is sort of a difference in the units of these two, and that becomes kind of important a little bit later on in this chapter because we will see a formula where we use them together. So again, if you use them together in a formula, you want to make sure that you got everybody on the same sort of units. Otherwise, you'll be off by a factor of 1,000. Now, disorder is related to probability. A probable event is one that can happen in many ways. A sort of improbable event is one that could happen in only a few ways. A ordered state has a low probability of occurring and has a small entropy. A disordered state has a high probability of occurring and a large entropy. So what's that old saying? You know, there's many ways to screw things up, right? So there's a lot of ways to screw things up. So there's a high probability that you might screw something up along the way, and that would have a large entropy value. As opposed to there's like only one of a few ways to do things the correct way, right? So there's odds are you might not do it the correct way. So that's a low probability of happening and a smaller entropy that could happen. Now, entropy can be related to what is sometimes referred to as microstates. And that is what the W stands for here. The W is the number of microstates. That is the entropy, and the K is down here, which is a constant that is Boltzmann's constant down there. So we could use the number of microstates to help us decide, you know, what the entropy would be. So for example, if we had 4 circles and 2 sides to put them on, if we wanted to put all 4 circles on one side, there's pretty much only one way to do it. Either you put it on the left-hand side or you put it on the right-hand side, but very much one way to kind of do that. If you want to put kind of 3 circles in one circle in the 2 ways, there's 4 ways of doing that. And if you want to go 2 circles into each, there's kind of 6 different ways that you could do it. It is much probable, right, that this will occur, right? There's a higher chance that that will occur than here. If you think of it like a carnival game, you got to get all 4 balls into the left-hand side there, right? Probably a low shot, better shot if you just need to get 2 on each side, right? An easier probably way to doing that. And if we think about mathematically, if we put it into sort of this Boltzmann equation here, the S is equal to K natural log of W. With our W being 1, that would give us S is equal to K times the natural log of 1. Natural log of 1 is equal to 0, which means our entropy here is 0, pretty low in terms of the entropy. As opposed to if you did 6 here, ignoring the constant, natural log of 6 is something like 1.8 or something like that. So we have a much positive entropy value here and a much higher entropy value because, again, a lot more disorder happening here than everybody nice and neat on one side of the table. Any questions on that there? Again, some very common processes that lead to that increase in entropy. As we talked about before, melting our solid can cause more disorder. Obviously, we take liquid and turn it into gas. That creates a lot more disorder. The process of making a solution is one that creates a lot of disorder. Before you take something like a ionic solids are put together in a very ordered or unordered fashion. Ionic solids are very ordered, yes. Like, you know, maybe you learned about it last semester. Cubic squares, yes. Unit cells, simple cubic. Anyone? No. Maybe they don't teach that anymore. I don't know. But they're very, very ordered ways. And obviously the solvent, like all the water molecules, which are all together, are also hydrogen bonded together, for example, if it's water, in a very organized sort of fashion. So in order to get everybody to dissolve, you got to break apart the solvent, you got to break apart the solute, which is both parts of a solution. And now you have a lot more disorder with everybody sort of intermingling together, increasing the energy, increasing the amount of entropy. Temperature as well. If we increase the temperature, that definitely will create a lot more disorder. When we increase the temperature, things move slower or faster. Typically faster, which means they light a fire under you, you start running around crazy, right? Same idea, right? A lot more energy, things flying around, a lot more. Everybody has more energy. It's going to create a lot more disorder than at a lower temperature. All right, so let's take a look at each of these and decide. So how does the entropy change for the system? And each of the following, does it increase or decrease? So take a moment or two for each of these examples and decide what is happening. Okay, let's take a look. So condensating water vapor, condensation means we are going from what state to what state? We are going from gas back to liquid, right? That's condensation. That means that we're going from gas where everybody's flying around a lot, right, to liquid, which is definitely more order, right? Less disorder. That means that we would expect our entropy value here to become negative as the order is increasing in this case. The disorder is obviously decreasing. Again, however way you want to look at that. Any questions on that one there? Forming a sucrose crystal from a supersaturated solution. The key word here is a crystal. Crystal is a solid, which is probably very well organized. And that also would decrease the disorder, right? It would also obviously increase the order. And that means that the delta S here would become a negative value. So again, as order increases, delta S becomes negative. Heating from 60 to 80, that increase in temperature is going to cause everybody to fly around a lot faster, obviously increasing the disorder and decreasing the order. That moves our delta S into a positive sort of change. And lastly, sublimation here, dry ice sublimation is going from solid directly to gas, skipping the whole liquid intermediate there. That obviously is going from solid where everybody's ordered to gas where everybody's flying around. And again, that should definitely increase the disorder here and result in a delta S that is more positive now. Any questions on any of those there? So entropy is a state function. And as you might remember, probably from your conversation in Chem 50, state functions are properties that really doesn't matter how you get there, right? And really the only two things that are really important is where you start and where you finish. That's basically the two important parts. That's why we calculate things like final minus initial, right? Final where you ended, initial where you started. Things like energy, enthalpy, pressure, and entropy are state functions. This is an example of potential energy. Both hikers started there in the same spot. They ended in the same spot. The blue guy took the more direct route. The red guy took the scenic route around the mountain. In terms of their potential energy, it really doesn't matter how they got there. It just matters where they ended and where they began, which is why we again take a lot of times final minus initial when we calculate like the change in energy, the change in enthalpy, and even the change in entropy. We do our final minus our initial. So it is a state function, as why, again, when you dealt with perhaps enthalpy, you did Hess's law, which is everybody's favorite, right? Take a whole bunch of individual reactions, add them together, and you get the overall reaction. And you just add up all the energy, right? Final minus initial. When we think about a chemical reaction, our final state is our products, right? And our initial state is our reactants. That is why a lot of times when you calculate these things, you take products minus reactants, because products is final state, reactants is initial state, and that's why we calculate these things. Delta S can be looked up in a table with other things like thermodynamic values. There are, again, a couple things that are different than, say, the delta H values that you would look up. And there's a couple of things that you want to do kind of similar to what you would do. So if you remember maybe using a delta H table, when you go to that table, it's really important not only to find the substance that you're looking for, but to also find it in the correct state. So water is a very common one, solid, liquid, gas. So you want to always make sure, definitely with entropy as well, you do the same thing. You find it in the correct state. The other major difference, as I mentioned, was units. Again, H will be kilojoules. When you go to the table here for S, it will be joules. The other difference as well is entropy is typically all positive numbers when you go to that table. So when you go to that table, they're all positive numbers. The other thing that's a major difference is if you go to like a delta H table for something like O2, H2, the values will be 0. Yeah, so they have 0 for those. But if you do that for entropy, you will actually find values. So you'll have values for things like O2, H2, things in their standard sort of state. So there will be some entropy values for those, which is different than for delta H, where they're typically going to be 0. Just like normal, we'll talk about it. You can calculate the delta S by taking all the entropy of the products minus all the entropy of the reactants. You would multiply, obviously, by the coefficient as well to do so.